All right, so this is section 4.4, properties of logarithms, solving exponential and logarithmic equations. So we've already kind of talked about logarithms some, right? And graphing them and how they relate to exponentials and such. So in this section, we'll actually do a little bit more with logarithms and dealing with them in equations and such. So first, we should kind of recap some of the fundamental properties of logarithms. So for any base that is above 0, remember that having the negative in there just means a reflection, so it doesn't really change anything. Then b cannot equal 1 because that's the trivial case, right? So our first one here is that if we have log base b of b equals 1, well, that means because it's the same base, right? Base b of the log and base b of the inside, kind of the exponential portion, right? Because, remember, we do base to the answer equals the inside, all right? So that's how we get this, the exponential version, right? Then the second one there is if log base b of 1 equals 0. Well, that's because, again, b to the 0 equals 1, right? It's circular. So anything to the 0 equals 1. So it doesn't matter what that base is. Then we have this one, same base, right? So kind of they cancel out and the x is left. Or again, you can take b to the x equals b to the x, right? Then this last one, this one's kind of the reverse of number 3, right? They both equal x, it's just which one's inside of which. So number 3 has the exponential inside of the log, right? It's kind of log and then exponent inside of it. This one is exponent with log inside of it, okay? So that's why it's base b to the log base b. Those cancel and we're left with x. That's why it equals x, right? So this is kind of the exponential version and this is the logarithmic version kind of thing, basically. Okay, so those are our basic properties, okay? Let's use those in an example. So for this first one, you always want to get the kind of x term on its own first, right? So that means, well, we want to take that 29 over. So we have 10 to the x equals 51 plus 29, that's 80, right? Then we have base 10. Well, base 10, if we take log base 10, or just log, because, well, if you don't write the base, it's assumed base 10, right? These cancel, that's that third property. So then this is x equals log base 10, right? Or don't write it, of 80. Well, that, if we plug that into a calculator, because there's no real way to know these always, this is approximately 1.9031, okay? So now let's do this next one. This one again, get the x term on its own first. So add the 5, so we have 3e to the x plus 1 equals 12. Then divide by 3, get it completely on its own. So e to the x plus 1 is equal to 4. Now, if we want to counteract in base e, we must use the natural log, right? So these cancel, and we're left with x plus 1 is equal to natural log of 4, and then we can subtract the 1 over, right? Now make sure this is ln of 4 minus 1, right? Don't subtract and make that ln of 3. We cannot reach that inside portion of the ln, okay? So then this is approximately equal to 0.3863. using a calculator again. Okay, so that's some basic ones. Let's, these are both starting kind of exponentially, right? And we have to use a log. Let's start out with logs now and have to use exponentials probably. So again, get the term on its own. So that means get the log on its own. So we want to subtract the 1. So we have 2 log of 7x is equal to 3. Divide by 2. So we have log of 7x is equal to 3/2. Now, remember, this is a log, right? The opposite of it is how you get rid of it, okay? This is not division. This is not log times 7x. This is log of 7x. It's like a square root, right? So we cannot do anything with it except to get rid of it with its inverse, okay? So it's always the same base. Put in an exponential, right? So this log doesn't have a base written, so it's understood base 10. So we say 10 to this side equals 10 to this side. So these cancel. So that means we have 7x equals 10 to the 3/2. Then we can divide by 7. So x is equal to 10 to the 3/2 over 7. This simplifies a little bit, right? That we know 10 cubed is 1,000, and then we would need to know the square root of 1,000 and then divide by 7. So we can actually just know that this is approximately equal to 4.5175. Okay, so you would need to be able to solve these out before we can put them into a calculator, right? Because otherwise that x is right smack in the middle of what you'd want to put in. All right, and there's no real good way of guessing on these either. Okay, so then for the next one, again, get the x term completely on its own. So -4 natural log of x plus 1 is equal to 12. Divide by -4. So natural log of x plus 1 is equal to -3. But is that possible? Can a natural log equal a negative number? Well, let's think about that, right? Think about our graph. So if we have the log graph, that looks like this, right? Thinking from the last section. Well, yeah, we can certainly have that, right? Then because we can get negative values right here. So this is okay. Negatives are not always bad, just sometimes. So it is good to think about them though. All right, so from here, that means we have natural log. This is base e. So e to this side equals e to this side. So cancel out the e and ln. So we have x plus 1 is equal to e to the -3. Then we can subtract the 1. So x is equal to e to the -3 minus 1, which is approximately -0.9502. Okay, so that's dealing with kind of the basic properties of logarithms. Now let's get into kind of being able to do a little bit more with them instead of just kind of solving and just kind of, okay, getting rid of it or putting it in, as the case may be. Let's actually be able to do some things with logs. So this first one relates back to the multiplication exponential rule, where you multiply same base, right? Different exponents or same exponent, doesn't really matter, but just same base. You multiply and you add the exponents, right? So remember, exponentials, which is what that was, and logarithms are inverses. So they should do the opposite, right? This one, the exponential rule is multiplying on the outside and adding on the inside, right? So we should do the opposite. We should multiply on the inside and add on the outside, right? Okay, so if we want to prove this, let's start off with the actual log rule here. okay? So we have log base x of AB, and we want to show that it equals log base x of A plus log base x of B. So now if we want to kind of use the exponential rules, right? That means we have to use that same base. So that means the base is x, so x to the one side equals x to the other. All of this and all of this, okay? Now, this is a single log with a single exponential. These can straight up cancel, okay? So now that means we have AB equals something. Now what can we do with this? We know that addition within the exponent, well, that can be broken up to be two separate exponentials, right? So that means we have x to the log base x of A times x to the log base x of B, right? Well, now these will cancel. So that means we have AB equals A times B. Well, that's the same thing, right? So we just proved this rule, okay? So that means, let's show it concisely here and in the kind of a little bit better format. So log base b of x plus log base b of y is equal to log base b of xy. So addition on the outside means multiplication on the inside, okay? So then the next rule. If we look here at this one, this also kind of makes sense again, right? We start with division in the exponents with the exponentials, right? Same base, means we subtract. So if we divide on the inside, that means we subtract on the outside, right? This proof is very similar to the last one, but we can go ahead and do it out. This would, again, start with the log rule. So log base x of A over B is equal to log base x of A minus log base x of B. X to both sides entirely. So then these cancel, so we get A over B. This one we can again rewrite using exponential rules as x to the log base x of A over x to the log base x of B. These cancel, right? So then that means, again, we have A over B equals A over B. So we just proved it. So again, more concisely, is log base b of x minus log base b of y is equal to log base b of x over y. Okay? So then we have a third one. This is that layered exponents, right? So x to the a, all to the b. That just means you multiply the exponents, right? Well, it's a little bit different with logs. If we have log base x of a to the b, that means we can take that exponent and multiply it down out front to make it b times log base x of a. All right, so again, let's start off with log base x of a to the b is equal to b log base x of a. So x to both sides again. Now, this one we have to finagle a little bit, all right? If we have x log base x, those just cancel, okay? So all we're left with is a to the b. Now this side we have to think about a little bit. We have multiplication within an exponent. Just undo it again using the exponent rule, okay? So that's x to the b. Sorry, I went it the other way. X to the log base x of a, right? We want to keep the base x exponential and base x log together, all to the b power. This is just multiplication. It doesn't matter what order it's done in, right? So we can bring whatever we want to the outside exponential portion. So these log base x's cancel. So this is still a to the b. Then this side, only this a drops down. Okay, so that a drops down, this b is still in the exponent, so it's a to the b. Okay, so there's that proof. All right, so again, stated better, we have log base b of x to the a equals a times log base b of x. So here's just the properties restated with one extra one. This fourth one here is called the change of base formula. Okay, so that means this b here, we don't like that as our base because calculators, we can't input bases that we want, all right? So that means we can change it to any base we want using this formula. So generally that's going to be either a log base e, because that's natural log, right? We have a button for that, or log base 10, because again, we have log base 10 in our calculators. So this would be, right, if we have log base b of x, you take the inside one and put it on top. So it's log base whatever you want of x over log base same base, okay? That's very important. Then this, the base of the original, is the inside of the bottom one, okay? So it's log of inside over log of base, okay? All right, so now let's use some of these. This first one, part A, we see we have the same base, which is very important. We have addition on the outside, so that means we multiply on the inside, right? So this inside is, well, log base 2 of 45, right? 5 times 9. So now this one, part B, we have, again, same bases, important to see, right? We had now subtraction in between them and division inside. So that means we just use that log rule, right? So the top is this first number, so it should be a 7. Now, this one's a little tricky, right? Let's go ahead and rewrite this one out with a x as the unknown portion. So this x is what we want to know. So let's kind of move it around a little bit and see what it could be. We have log base 5 of 1/4 is equal to, now we want these log base 5s to be exactly the same. This one has a coefficient, this one doesn't. Let's move it up. We have a rule for that, right? So this is now log base 5 of x to the negative 2. All right, so that means these log base 5s can cancel because they're the same thing on the outside. So that means 1/4 is equal to x to the negative 2. Well, we can rewrite x to the negative 2 as 1 over x squared, right? That means that 4 is equal to x squared. So then x could equal plus or minus 2. Those are not our solutions though, okay, because we have to check them. So, can we put in a negative input into a log? No, right? Because our domain is 0 to infinity, not inclusive because of that asymptote. So we get rid of the negative, and our only solution here is 2, positive 2. Okay? So next example is we want to use the properties that we just proved to expand the following expressions: no radicals, no exponents. Okay, so first we have a multiplication and a division, right? Multiplication here, division here. So that means we can expand these. So log base, just leave it as base 10. So log of 6, multiplication converts out to being a plus. Log of x plus 5 squared. Division is a minus. So log of the cube root of x to the 4th. Okay, next thing to do, log of 6 is just log of 6. So then this exponent can come down out front to be 2 times log of x plus 5. Now, this is an exponential, right? Because this is technically x to the 4/3, right? So then this is minus 4/3 log of x. We have no radicals and no exponents. So that's our answer, okay? Don't change this one. This does not equal 2 log x plus 2 log 5 or 2 log x times log 5. Does not equal either one of those. We cannot do anything when we have addition on the inside. It's just addition on the outside or multiplication on the inside, right? So don't make that mistake. Okay, so this is our final answer for this problem, okay, and how we would leave it. So then, next problem, we want to write this one as a single logarithm. So we're kind of going backwards from the last one. So first thing you want to do is have no coefficients. All right, so that means that first 1/2 needs to come up. So it's log base b of y to the 1/2 plus that 7 also needs to come up. So log base b of z to the 7th. Then this one's fine, just minus log base b of x. Now we can combine, right? So this one is a plus, so their insides get multiplied. So we have log base b of y to the 1/2 times z to the 7th over, because of the minus, it's division, right, of just x. Now you could leave it like that, that's perfectly okay, or if you really want to, you can make it log base b of the square root of y times z to the 7th over x. Okay, just be careful if you do this last step that only y is inside the radical, right? Not the z to the 7th. Okay, next example. We want to find the value of x. So that means we need to figure out what the heck is going on, right? So first, we really don't like that log, right? So let's do a base 8 to get rid of it. So we have 8 to the log base 8 of 11x plus 2 equals 8 to the 15th, right? So then those cancel. We have 11x plus 2 equals 8 to the 15th. Okay, so then what? Can we do this? No, right? We could then take a log base 11, but we don't really like that. So this was actually not the best step to do. We don't want to do it that way, all right? What we want to think here is, oh, well, what rule did we just figure out? That third one, when we have exponents inside, we can bring it down out front. So this is really x plus 2 times log base 8 of 11 equals 15. So then this is x plus 2 is equal to 15 over log base 8 of 11, and then subtract the 2. So this is x equals 15 over log base 8 of 11 minus 2. Now, to put this in the calculator, we will need to change base, right? That fourth rule. So this is 15 over log of 11 over log of 8, all minus 2. Now, make sure do this all in the denominator of the 15, okay? You should get approximately 11.0079, but they want nearest thousandths, so we will round that to 0.008. Okay, so that's that problem. Next is this one. This setup here is if we have multiple logs and they have the same base, but we have this other 3 there, that plus 3, that we don't really like. It messes things up. So let's take the logs to the same side. So this is log base 2 of x plus 5 plus log base 2 of x plus 3 equals 3. Well, this is addition on the outside. That means we can multiply the insides. Log base 2 of x plus 5 times x plus 3 equals 3. Well, now we can do that trick that we were trying to do last time. 2 to that side, 2 to that side, these cancel. Let's FOIL this out. We get x squared plus 8x plus 15 is equal to 2 to the third is 8. Subtract it over, so x squared plus 8x is then plus, what is that, 7 is equal to 0. So this factors into x plus 1 and x plus 7 is equal to 0. So we then get x equals -1 and -7. Always check your answers though, especially when you get multiples. If we plug in -1, -1 plus 5, that's positive, that's okay. -1 plus 3, that's still positive. That one's okay. Now, -7. -7 plus 5, that's not positive. So we cannot use -7. So that means our only answer on this one is x equals -1. Okay, another example. This one is more exponential, right? We might have even seen this one or similar ones before. We have to get the bases the same though. So we can write 16 as a base 2. That's 2 to the 4th. But it was already to the 5 minus x. And this 2 is to the x squared minus 18x plus 16. Sorry, I don't know where I got 16 from. 65. So we can multiply these exponents, and same base means they cancel, right? So this would be 20 minus 4x is equal to x squared minus 18x plus 65. So then 0 is equal to x squared minus 14x plus 45. So this factors into x minus 5 and x minus 9. So x equals 5 and 9. Now if we check these, they both work, okay? It is important though to check them all the time. So this one is kind of gross because they are different bases and they're not something we can rewrite in the same way, right? In the same base. So that means we have to use log rules, right? Well, we want to use base 10 logarithms. That's okay. We can do that. Just take log of both sides. Then we can use the exponent multiplication rule, right? So we have 5x times log of 2 is equal to -x minus 7 times log of 3. So this one stays as 5x log of 2. This is now -x log 3 minus 7 log 3. Well, take this one over because we want to get all the x's on the same side. So 5x log 2 plus x log 3 equals -7 log 3. Now, factor the x out, right? So x times 5 log 2 plus log 3 is equal to -7 log 3. So that means x is equal to -7 log 3 over 5 log 2 plus log 3. And that would be our final answer because they wanted it in an exact answer format. Okay, last example. This is an exponential quadratic equation. Notice because we have 2 here, 1 here, and 0, basically, kind of thing, e to the x is here. So if we want to, we can think about it as e to the x squared minus e to the x minus 6 is equal to 0. Well, we could, if we wanted, do a substitution. So this is y squared minus y minus 6 if e to the x equals y. If you don't need to, if you see it here, that's fine. You don't need to do that substitution. So this factors into y, let's see, minus 3 and y plus 2. So that means y is equal to positive 3 and negative 2. Well, can e to the x equal both of those? Can e to the x equal 3? Well, sure, yes it can, right? So that one's good. Take him further, right? So take the natural log of both sides and get x is equal to the natural log of 3. And then solve that out to the nearest hundredth. But can e to the x equal negative 2? No, there's no exponent that will give us a negative number, right? So this one is off the table. We only have this solution rounded down using a calculator. So that is section 4.4.